how you could achieve 50% yearly returns on US stocks with AI. In this video, you'll find explanations of this hybrid forecasting algorithm combining the best of both worlds, LLM and XGBoost. To get the full code and proofs of my results, check my GitHub repo in the description. You'll be able to reproduce the results and train your model on the specific assets you're targeting. The code is written in standard Python, comes with all instructions, and doesn't require expensive hardware to run. This algorithm is powered by FMP Modeling, a great data provider, and it comes with code to execute orders directly through interactive brokers. Here is a big picture of this hybrid model from the data pipeline to the predictions for a given stock. At the input stage, a single data provider lets us retrieve news, fundamental ratios, technical data, and institutional ratings for hundreds of stocks. Then there's a lot of feature engineering to prepare the X part and transform this in time series, filtered, denoised, normalized to provide best possible prediction quality. A standard XGBoost model provides final predictions. At XGBoost output, normalized predictions form the foundation for managing portfolio allocations. Now, let's walk through a crucial step, preparing the X time series at inputs. News arrives in an unstructured format, so we need to extract sentiment at the global level, at the company level, and for its competitors. Then we convert that information into a structured scoring time series. This can be achieved with a commercial LLM API, using a prompt that scores sentiment on anonymized news across different topics on a daily basis. An important task is to filter out websites that do not provide time-stable content, so we only keep information as it was originally reported for prediction. Other data coming from FMP are structured, but we still apply normalization and filtering to retain only the original as reported figures, which helps optimize predictive performance. Looking back at the global view of our model, we need supervised data to produce a reliable prediction. In our global view, we have an output called y. This variable represents the supervised data, the ground truth. Y hat is the prediction generated by the model. Our first step is to extract label from data, and in this case you're lucky, as it's quite easy to do this for stock prices. We take different moving averages, then we analyze how these moving averages cross each other, as you can see in this animation. We assign bool and bear classes to crossovers that last longer. Another, without trend, is simply set to range. This allows us to generate our supervised variable y easily and in large quantities. During the training phase of the XGBoost model, loss function will compute error from y hat and supervised y. And of course, during the inference phase, we only rely on the predicted value, y hat. If we want to train a model that performs very well with a time series by reducing errors on unseen data, feature selection is a key step. It is essential to denoise the data and remove features that hold no predictive power over time. These features only introduce noise and overfitting, leading to an immediate loss of performance in the future. At this stage, it's important to capture as many market phases as possible over the widest possible time horizon. We can break this horizon into two separate segments. Here we show two periods, A and B, but in practice it could be 3 or even 4 periods to perform this operation. We can train model on these separate segments and check the feature importance across them. Then we look at the ratio of the mean importance divided by the standard deviation of that importance. With this method, we can easily identify which features maintain a significant importance over time, and which ones, across different periods, consistently lose their relevance. Of course, the features that behave in a stochastic way through time will be removed. We can see that the ratio of the mean divided by standard deviation of that importance can help to establish the most relevant features rank. From there, we can train the model by gradually adding features following this rank until we reach the maximum test performance. This ranking significantly boosts the model's performance, but it still comes from an intuition. We can refine this ratio further by introducing an hyperparameter p, which allows us to adjust the exponent applied to the standard deviation. Then you can search P across a relevant range. To find better models, these features, reordering and filtering procedure can be applied iteratively as long as it continues to reduce error on the test set. In practice, we can go from about 350 features down to 50 or 60 to reach the ultimate best performance on the test set. There's still a crucial step ahead, using output predictions to open and close positions at the right moment. One way to use the model is to track how the bull probability evolves and then identify the thresholds that allow us to optimize when positions are opened. And we use the same approach to find the best threshold for closing long positions. The exact same logic applies to short positions as well. Finding thresholds that optimize the opening and closing of positions for all types of stocks across all market eras is anything but simple. Even though XGBoost is a very strong model for this stage, it cannot be used with reinforcement learning, which prevents us from directly training the outputs to link them to position taking. And on top of that, we still need to manage the selection of the best positions among the 100 stocks being monitored. To implement this strategy, we need to search for thresholds over a wide range of time and across many stocks. This is why we use two alternating intervals, A and B, which allow us to run a continuous backtest without ever using a segment that was involved in training. So the idea is to train two models, A and B, each one trained and tested on opposite time intervals. This strategy also gives us the ability to optimize the thresholds so we can manage multiple positions at the same time. Handling two models is not a source of complexity. We simply switch between the models along with their associated threshold sets depending on which interval we are in during the backtest. Now let's see how we can build a backtest function that manages both models, A and B, along with their respective parameter sets. This function will simulate traits over the entire historical period using the thresholds defined in each parameter set. We'll see later how this backtest function can be used by an optimization method to search for the best possible A and B parameter sets. We run a day-by-day loop over the entire backtest period. We select model and parameters A or B according to the current time interval defined by the current day. We calculate the signals to open the best long or short positions depending probabilities and parameters. We compute the signals that tell us which positions should be closed. Open and close positions according to signals, existing positions, and available capital to invest. Next, we calculate the current portfolio size by adding the remaining capital and open positions values. Then we return an overall performance score for this backtest, which allows to compare different runs with different parameter sets. To find the best parameters, set A and B, that maximize the overall performance of the backtest function, we need a stochastic optimization method suitable for non-differentiable functions. CMA-ES is a stochastic optimization algorithm. It's not a gradient descent method. Instead, it explores the search space by sampling from a Gaussian distribution that is continuously adapted. In this animation, you can see how the method optimizes a two-dimensional quadratic function. Of course, here we will plug in on backtest function. The goal is to maximize it using a performance measure that reflects the investor's specific profile. Here, for example, we want to maximize returns while keeping drawdown under control. A very important aspect that helps secure the search is to organize all parameters so that increasing a parameter value always corresponds to selecting more qualitative opportunities. This way, you can multiply all your search parameters by your performance score. It helps keep solutions where the algorithm may find an equivalent performance with higher parameter values and therefore favor safer configurations. After completing the hyperparameter search, we obtain this backtest performance, which consistently outperforms the Nasdaq shown in orange. The multiple portfolio curves come from random stock lists that change each day, providing a Monte Carlo style evaluation. The blue, red, yellow, and orange curves represent the results when all stocks are available for trading. The cutoff training date for XGBoost is shown by the red dashed vertical line. The cutoff finite tuning date of CMA ES is shown by the orange dashed vertical line. After this date, the model continues to progress in a consistent way, whereas all cutoff dates are passed. If you enjoyed this content, don't hesitate to support me and see you in the next video.